Good evening, everyone. I am Usman K, Assistant Professor, BITM Ballari. First, I welcome you all to my second video lecture on Model 4. So, in the previous video lecture, we discussed what is three-dimensional viewing and how three-dimensional viewing concept is. It is similar to our real camera. So we discussed a few terms with respect to real camera as well as our synthetic camera. So in the previous class, I said three-dimensional viewing is a process of displaying three-dimensional object in a space on a two-dimensional display device. So this is the simple definition of three-dimensional viewing. So when we are using three-dimensional viewing, I also said that here we are using clipping volume to display a three-dimensional object on a two-dimensional display device. So today I would like to introduce what are the terms we are using in three-dimensional viewing. So before introducing few terms with respect to synthetic camera, we already know these terms in our real camera. So whenever we want to capture any image by using real camera, first we need to decide what is the position of the our real camera. Second, we need to decide what is the orientation of that particular camera. Next we need to decide once I capture that image, where I need to display that image with respect to real camera. So when we are using real camera, the captured image is projected on a camera film, and finally it is displayed in a two-dimensional photograph. So we are using lens there, we are using camera film, and we are using the clipping window, that window. All these concepts we are using in our real camera. Today I would like to introduce how we are using synthetic camera concepts in a three-dimensional viewing or in computer graphics. So when we want to introduce synthetic camera model in OpenGL, I need four steps. First step, I supposed to define the object position in the world coordinate system. So I written first point, define world coordinates description of the object. So assume that there is a one object exists in the world, and that object having its own mathematical description, and we are providing the position of that particular object in a world coordinate system. So this is the first step we need. So once you define position of the object, second step is we need to define position and orientation of the our synthetic camera. So defining position of the synthetic camera or orientation of the synthetic camera, we need to consider it is viewing coordinate system. So first I defined object position, second I defined position of the camera. Third step, we need to map object that is present in the world coordinate system into the camera coordinate system. So once you perform transformation of world coordinate system to viewing coordinate system, then we can project three-dimensional object onto the two-dimensional viewing plane using projections. So these are the four steps we need when we want to project a synthetic object of three-dimensional onto the two-dimensional screen. So I will repeat. First step, define position of the object in world coordinate system. Step 2, define position and orientation of the camera called viewing coordinate system. Third, perform transformations of world coordinate system to viewing coordinate system. Viewing coordinate means here camera coordinates. So once you perform mapping with respect to world coordinate system to viewing coordinate system, finally you use projections concept to display three-dimensional object on a view plane. View plane is nothing but, it is nothing but one virtual plane. On the virtual plane, we are projecting image with the help of projectors or with the help of projections. So these are the 4 steps we need when we want to display any three-dimensional object on the screen of the monitor. So we'll see step by step how to represent position of the object, how to represent position of the camera. We will see step by step. So we'll go to first step. First step. So see that here. In the first step, I defined I have one object in the world space. In the world, assume that one house is there. So if any object is there in the space, we know that every object in the world having its own coordinates. So assume that there is a one house is there here. This house I specified its position in a world coordinate system. So world coordinate system means we have x-axis, we have y-axis, and we have z-axis. So here I specified position of the three-dimensional house in a world coordinate system. So after specifying position of the house in world coordinate system, I need to define or I need to specify where I located our synthetic camera. So as you can see that I located synthetic camera here. Please you see the mouse pointer. I located synthetic camera here. So this camera is also having its own coordinates, but those coordinates is called viewing coordinate system. Means I need to determine what is the coordinate position of this camera. So the coordinate position of this camera is nothing but viewing coordinate system. So I'll repeat, object is located in a world coordinate system and camera is also located in a viewing coordinate system. So here I defined what is the position of the camera and what is the orientation of the camera with respect to viewing coordinate system. So as you can see the second diagram, in the second diagram, I am highlighting any object can be represented in a world coordinate system. So that object having x-axis, I represent in a red color, y-axis I represent in a green color, z-axis I represented in a blue color like this. So assume that we are defining our object in a world coordinate system. When you define this object in a one world coordinate system, to capture this image, I need to define our camera position also. So defining camera position is nothing but defining viewing coordinate system. So as you can see that here, I written one diagram right side. So A represent, we are looking towards the object. E represent here, that is called I. R, we kept camera here. I will repeat. So E in this arrow represent, we kept camera here and we are looking towards the object called A. So A is nothing but our reference point. Means we are seeing towards the direction called A, and this direction is nothing but viewing direction. So we need to specify in which direction we are viewing, because here we are implementing synthetic camera. So that synthetic, if you are using synthetic camera, you need to specify what is your viewing direction. You need to specify what is your position of the camera, and you need to specify what is the orientation of your particular camera. So these all are the things I need to specify virtually, means with respect to code. With respect to coding, I need to define all these parameters. So here we are implementing actually synthetic camera. So our object is there, we are capturing that object using synthetic camera, and once you capture that image, we are displaying that captured image on the screen of the monitor. This is nothing but our three-dimensional viewing concept. We'll move to next slide. Now, in the previous slide, I defined our object position in a world coordinate system. With respect to this slide, you assume that we need to define position of the camera. So if you want to define or specify position of the camera, I written heading is three-dimensional viewing coordinates parameters. You can say either three-dimensional viewing coordinate parameters or three-dimensional camera coordinate parameters, or you can also say that eye position parameters. Eye is nothing but we kept our camera there. So wherever camera is there, it is nothing but our eye is there with respect to that camera. So now we need to define what are the parameters that comes into a picture with respect to viewing coordinate systems. Whenever I am telling camera coordinates, means it is nothing but viewing coordinates only. Or here I written clearly it is xv, y subscript v, z subscript v. So xv, yv, zv is called viewing parameters or viewing coordinates of the camera. So when we want to define camera coordinates, we are using few terms with respect to our synthetic camera. So like how we are using like terms like film, like lens, like clipping window. Uh, these all are the terms we are using with respect to real camera to capture the image and to display that image on the film. Same terms we would like to use in synthetic camera. So let us begin. What are the terms we are using with respect to synthetic camera? So first step is I written here to set up the viewing coordinate reference, or to set up the viewing coordinates of the camera, we need to do we need to execute following steps. We need to define position and orientation of a view plane. So yesterday we discussed, or in the previous class we discussed, what is view plane like this. View plane is nothing but displaying three-dimensional object on a projection plane. So displaying three-dimensional object on the projection plane is nothing but three-dimensional viewing. So this view plane, it is similar to our camera film. View plane is nothing but is similar to camera film. Means once the image has been captured in the real camera, with the help of that light sources, the reflected light enters inside the camera and it will start projecting one captured image on the film of the camera. So like that only, in real camera we are using camera film to display or to project the captured image. But in case of synthetic camera or in case of OpenGL, we are using view plane, or we are using virtual plane, or we are using projection plane to project the three-dimensional object. So to project the three-dimensional object, we need to specify what is the position and orientation of the projection plane between the camera and our object. So this is the settings we need to do when you are using synthetic camera. So I repeat, first we need to define where you are placing virtual plane or projection plane between the camera and object. This is the first setting we need to do, or first we need to define position of the projection plane. Next point I written clearly, objects are transferred to the view reference coordinates and projected onto the view plane. Means with respect to position of the camera, the captured image is projected onto the projection plane. So this is the purpose of using projection plane in synthetic camera like this. Now as you can see that here, with respect to these 2 points only I am explaining. Assume that there is a one three-dimensional object. It is specified in a world coordinate frame, means world coordinate system having x-axis, y-axis and z-axis. Now we want to capture this image by using synthetic camera. So we located here synthetic camera. So if you placed a synthetic camera here, we need to determine what is the coordinate reference frame of the synthetic camera. But I will discuss how to determine within camera coordinates. Camera coordinates means how to determine camera coordinates means x view, y view, z view. These are the three coordinate axes with respect to camera. How to define, I will discuss this in the next slide. Here I am discussing where to place virtual plane. Now with respect to first point, position and orientation of the view plane, here you can see that I placed one virtual plane, here one square, please you see the mouse pointer. I defined one virtual plane, this is called projection plane. When I capture this three-dimensional object, the captured object is projected on this square. This square is called projection plane or view plane. So now by seeing this diagram, you can see that we are looking or we are viewing towards the positive z axis. That red color is there. That red color arrow indicates that our z view is like this. Means our z view is that is moving towards the object. Means we are viewing, we are seeing that object in a positive z view direction. Positive z view direction. Right. So now I decided here what is the position of the projection plane. Projection plane is located between the object and our synthetic camera. Next here we decided what is our camera position. So we will discuss this in the next slide. Right. Now with respect to this slide, you assume that we specified what is the position of the projection plane. Next we will move to next slide. In the next slide you can see this here. Now what we need to do means here our aim is we need to define position of the synthetic camera. In the previous slide we defined what is the position and orientation of the projection plane. Now we need to decide where you placed synthetic camera. Where you placed synthetic camera means what is the position of the synthetic camera. So as you can see that one house is there. This house is present in the world coordinate system. So I can write here x-axis, y-axis, z-axis. This is the world coordinate system. Now as you can see that the position of the camera I kept within this direction. Means we are viewing this particular house like this. Means our camera is here. Camera is here. I specified three direction for the camera also. Means camera is also exist in the world only, in the space only. That camera is also having its three dimensions: x-axis, y-axis and z-axis. But for camera coordinates I will tell x view, y view and z view. And for the house I will tell it is there in the world coordinate system, that is called xw, yw and zw. Now please you see this diagram here. I kept house, the position of the house I am representing in the world coordinate, that is xw, yw and zw. This is the position of the house in a world coordinate system. Now I located our camera here. I located our camera here. So if you are defining position of the camera, you need to take one reference point for the position of the camera. So here I am taking one reference point P naught. So this reference point I have taken with respect to world coordinate, because whatever the camera I am locating, it is also present in the world coordinates only. So the, you see that here, you see this diagram, camera is located in the world only, but the camera coordinates are different and this object coordinates are different. If camera coordinates is also different, object coordinates is also different, then I need to represent those coordinates. So I have taken one reference point called P naught, and this P naught is I have taken, this is the one position or one point in the world coordinate system. What it is P naught? P naught is a, I am assuming it is origin of the camera, means in this particular position called X naught, Y naught, Z naught, I have taken, I fixed camera here. I fixed camera here. And the fixed point of the camera is nothing but P naught. P naught is a origin of the camera. I will repeat. I will repeat. If you want to define viewing coordinates of the camera, you need origin for that viewing coordinates of the camera. If origin is determined, from the origin only you can say that X view, X view, Y view and Z view. If origin is not there, you cannot able to set or you cannot able to tell what is the viewing coordinates or what are the camera coordinates. So only I have taken one point P naught in the world coordinate system that represent we defined or we fixed our camera at the point P naught. That is nothing but X naught, Y naught, Z naught. I can say that this is P naught is the origin of the camera. So once you defined origin of the camera, then you can tell that what is a Z view, X view and Y view. Again we have three coordinates for the camera also like this. Now let us begin with determining X view, Y view, Z view for the camera coordinates. So in the camera coordinates, here first we decided what is the fixed point or what is the origin of the camera. That is the first point. After defining origin of the camera, let's begin with determining what is the direction of the Z view, what is the direction of the X view and what is the direction of the Y view with respect to viewing coordinate system of the camera. Now if you see this first point, first as per the slide I written, first we need to determine viewing origin. P naught is called viewing origin, or it is also called viewpoint, or it is also called viewing position, or one more name is called eye position. Wherever camera is there, definitely our eye is there. Correct? No? That is real camera. But in synthetic camera, if you are fixing that synthetic camera at the particular position, it means that our eye is there or we are viewing that object from that particular point, from that particular point like this. That is called camera position or eye position or view point or viewing position. So first we defined what is the origin of the camera. So after determining origin of the camera, next we need to specify, we need to determine Y view, X view, Z view. So as per the diagram, I written here clearly second point, Y view is always view up vector of the camera. View up vector of the camera means Y axis. When you are capturing any image, the upward direction of the camera always represent Y view. So that Y view is called view up vector, and that can be represented one vector, unit vector called capital V, and it defines Y view direction. So we specified what is the meaning of Y view. Y view, it always gives upward direction of the camera. Next is, what is Z view? Z view always defines your viewing direction. As we have seen that in the second slide, or I'll go back to that particular slide. Please you see this arrow. This arrow indicates here our eye is there. Means this is nothing but our origin of the camera. If this is the origin of the camera, what is the viewing direction? This viewing direction, this arrow indicate Z view, and that is also positive Z view it is. We are always looking that particular object in a positive Z axis. Positive Z axis means that positive Z axis, it is coming out of the object. Out of the object. When you are viewing the any object through the camera, that positive Z axis, it is always coming out of that particular object. You need to assume like this. You need to imagine like this. Means that positive Z view, it is a direction with respect to camera. Or I can say that Z view is a viewing direction of the camera. Z view is a viewing direction of the camera. You can see that I written here along the Z axis, oftenly in the negative Z axis direction. Our best example is, please you see that instead of going to that particular slide, here one example I written here. Means I said clearly upward direction is called Y view of the camera. So we decided what is Y view. Now we are deciding what is Z view. Z view is nothing but, you see that here. We are viewing this house with respect to the position and direction of the camera is like this. Please you see the mouse pointer. When you are viewing this particular object in this direction, now you can see that this red color arrow indicate this is the direction of the viewing direction, but that arrow goes in the negative Z axis, towards the negative Z axis. And if the origin of the house is assumed that somewhere in the center of the house, if I draw one arrow, assume that I draw this black color arrow. Please you see the mouse pointer. This black color arrow indicates that Z view, that is a vector, or it comes out of the house. Means that is the direction of the camera. Means that is nothing but Z view. Z view is very important here. In which direction we are viewing the particular object. We are always viewing the object in a positive Z axis direction only, or positive Z view direction only. Now we decided what is the upward direction of the camera, that is called Y view. Next we decided what is the Z viewing direction, that is called Z view. So with the help of Y and Z, we can easily calculate what is the direction of the X axis. Right, by taking cross product, we can calculate what is the direction of the X axis. Now here I discussed what is the position of the projection plane. Next I defined viewing coordinates of the camera like X view, Y view and Z view. Next we will see one more term we are using, but that is already I explained, that is called view plane here. Means please you see this, with respect to this slide, I defined origin of the camera, that is A. Next I defined view up vector of the camera, that is called Y view direction, that is B. I defined viewing direction, that is called Z view, with respect to point C. After defining these three things, now I am defining how or what is the projection plane direction with respect to Z view. Now always the view projection plane, how we placed projection plane here with respect to Z axis means view plane is always, or projection plane is always, it is perpendicular to the Z view axis. Right. So as please you see that here, see this diagram, you will get the clarity. Here our camera is there. This camera having Z view, Y view and X view, these are the viewing coordinates. And the position, fixed point of the camera is nothing but P naught, or origin of the camera is nothing but P naught. Now if you are looking in this direction, for this object that is exist in the world coordinate system, then the position of the projection plane, it is always perpendicular to the z view axis. You need to remember this. You need to remember this. The direction of the projection plane or the direction of the view plane, it is always perpendicular to the z view axis. Z view axis. This is the first point you need to remember. The orientation of the view plane can be defined by a view plane normal vector n. So what is the normal vector means here? We need to draw one normal vector that should be perpendicular to the projection plane. So when you draw one unit vector called capital N, or it is also called normal vector, it should be perpendicular to the projection plane, but it will become parallel to the z view. So try to see the relationship between view plane normal vector n and z view axis. I said we kept projection plane perpendicular to the z view. How to analyze whether projection plane is perpendicular to z view or not means you draw a one normal vector. You draw a one normal vector n that should be perpendicular to the projection plane. When you draw that normal vector n perpendicular to the projection plane, definitely it will become parallel to z view. As you can see that, this is your normal vector v, normal vector n you drawn perpendicular to the projection plane. But this normal vector n, it will become parallel to the z axis. See that here, z view. When it becomes parallel to the z view, it indicates that we are viewing that particular object about the z-axis. So this is the position of the view plane or position of the projection plane with respect to z view axis. If you see this particular diagram here, there are three possible positions for the view plane along the z view axis. Means you can place the projection plane between the synthetic camera and object in three different positions. Please you assume, please you assume observer is standing here. Please you assume, I am explaining with respect to figure 10.9. Assume that observer is standing here and he is looking towards this direction. Towards this direction means observer is viewing towards the negative z axis direction. Please you see that here I drawn one Cartesian reference frame. Here we have x view, next to y view is there, and with respect to this origin, whatever the coordinate axis I drawn, this is called positive z axis and this is called negative z axis. Now assume that observer is standing here and he is looking towards the negative z axis. So when observer is looking towards the negative z axis, definitely object is present between the observer and this projection plane. Now where to locate projection plane means with respect to z view. As I said that projection plane always we will place perpendicular to the z view. So this is nothing but our projection plane and our z view is perpendicular to the projection plane. Now I can place the projection plane with respect to z virtual plane greater than 0, means with respect to positive z axis also you can place, or you can place with respect to negative z axis, that is z virtual plane less than 0. Here also you can place the projection plane, or you can place the projection plane that is parallel to the x and y axis, xy plane, parallel to the xy plane, means at the origin of the viewing coordinate system I can place the projection plane. What it means between the observer and object you can place the projection plane in three different places where z value is greater than 0. If z value is greater than 0, It means you are placing projection plane near to the observer. If you are placing projection plane in a negative z axis, means it is closer to the object. If you place the projection plane at the center or at the origin or at the xy plane, it will become parallel to the xy plane. These are the three different places are there. You can place the projection plane in three different places. So once you place the projection plane, that projection plane indicates what is the image has been captured through the synthetic camera. So these are the four things we decided in the previous example. I would like to repeat. First, we defined position of the projection plane. Next, we decided what are the camera coordinates axis positions. Means after defining position of the projection plane, we selected one reference point for the camera. That reference point acts like a coordinates origin of the camera. So from the origin of the camera, we started determining Z view axis. Next we determined what is the upward direction of the camera, that is called Y view. If you take the cross product of Z view and Y view, you will get the direction of the X axis. Next we defined our projection plane can be placed in three different places, and we said projection plane should be perpendicular to the our viewing direction. Our viewing direction is nothing but z view. How we can analyze that means I said clearly, draw a normal vector n. It should be perpendicular to the projection plane and it should be parallel to the z view. If you draw like this, whatever the image you captured from the synthetic camera, it is projected on the projection plane. So these are the few terms today we discussed with respect to viewing coordinate system or with respect to camera coordinates. So let us see one more example. So here, assume that there is a car and this car is present in the world coordinate system. So as a red color I written, this car is an object, it is present in the world coordinate system. Next I defined here viewing plane or projection plane. So this projection plane, it is a perpendicular to the z axis. Here I have taken z view, x view, y view, and we decided what is the p naught. P naught is a origin of the camera. Next, from the origin of the camera, we determined what is the z view, y view. If you take the cross product of z view and y view, you will get x view. So same thing here, we have a camera analogy. Here. Whatever the diagram I drawn here, it is a synthetic camera, you can assume that. Here, whatever the example I drawn, we are taking the real camera analogy and we are preparing. Now you see that here. Viewing coordinate system describe 3D objects with respect to viewer. Means whatever the object we are projecting on the projection plane, this is with respect to the observer. Observer means viewer. Now we need to define viewing plane, or we need to set up the viewing plane that should be perpendicular to the ZV, and it is aligned with respect to XY plane. It is aligned with respect to XY plane, or I said you can align in three different ways also. But with respect to this example, I am telling I can place the our projection plane parallel to the our XY plane. Then also we can project our three-dimensional object on a two-dimensional projection plane. This is a one example. Now see that here, how to determine. I am explaining once again all the concepts. So specifying viewing coordinates. Same story I am explaining once again. Now view reference point. First what we need to do, here I am explaining viewing coordinate system or camera coordinate system once again with respect to different example. So first we need to pick a world coordinate position called view reference point of the camera that acts as a origin of our viewing coordinate system, that is called P naught. So I said already, P naught is a point where a camera is located, or P naught acts like a origin of the camera. Next, the view reference point is oftenly chosen to be close to or the surface of the some object, or at the center of group of objects. So that last point is very important here. See, first I will explain real camera concept. In case of real camera, if I want to capture one image, assume that I would like to capture one image that is called group photo. If I want to take group photo by using real camera, in that group photo, always we will take one reference point as the consideration and then we'll capture. Not only the group photo, I am telling that in reality, when I want to capture any image or any object, in that object I will find out one reference point. Generally, when we will capture any image, the center position of that image we will consider as a reference point. With respect to that reference point, we will capture the image. Correct, no? The same thing, assume that I am taking one group photo. Assume that there are 11 members are standing in front of me. When I am taking group photo for the 11 members, among the 11 members, I will select the middle member is nothing but my reference point. So what I am telling means, when I want to take the group photo for the 11 members, the middle member I will take it as a fixed point or reference point. From that reference point only I will capture the image, so that all 11 member can be fit within that snap. So this is the one real life example I have given. When I want to capture the image, I need to take one reference point. Like that, in our synthetic camera also, when you are capturing any image, you supposed to take one reference point on the object. For example, here I had drawn one example here. If you want to capture cube, in that cube you take any pixel position as the reference point. From that particular reference point, you need to capture the image. So this is one thing we need to add with respect to synthetic camera. So same story is there. I don't want to repeat these things. Here we are viewing coordinates are there. P naught is nothing but our origin of the camera. Now after defining origin with respect to this slide, we are moving to this particular slide. In this slide, here we want to determine what is the Z view axis direction. So here I would like to explain one example how to select positive direction of the Z view axis means by specifying the view plane normal vector n. Means the view plane normal vector n decides the viewing coordinate, one of the viewing coordinate of the camera called ZV axis. Now what we need to do means, when we want to calculate Z view axis of the camera, assume that I am giving one example with respect to this diagram. Assume that there is a one pyramid in the world coordinate system, that is x world, y world, z world. Please you see the second example. There is a one object called pyramid. I want to capture this pyramid image and I located our camera here. So P naught is the origin of the camera, or our eye is located there. This is our synthetic camera position, and this is the position of the object in the world coordinate system. Now with respect to this blue color, please you see this blue color line. This blue color line tells what is the direction of the ZV axis. So what we need to do means, assume that we are standing at the position P0, or we located our camera at the position P0 and we are viewing towards this particular direction. Now if you want to determine what is the ZV axis, what you need to do means, if you want to capture this image, in this image I selected one fixed point, or I selected one reference point, that is called P. As I said in the previous slide, whenever you want to capture any image, in that image you decide one of the pixel position is your reference point, like group photo concept. Now in this pyramid I decided one point P is my fixed point. With respect to this fixed point, I want to capture this image. Then what I will do means, I will draw one normal vector, that is called n. I will draw one normal vector from this point towards the origin of the camera. This vector is nothing but normal vector or view plane normal vector. It is perpendicular to the projection plane. But it will become parallel to the our z-axis. As you can see that I drawn one arrow here. This is called unit vector. This is the one perpendicular line I drawn with respect to projection line. But I drawn this normal vector line from the point P2 towards the origin of the camera. When I draw this line will become parallel to the z-axis. So this line itself indicates our camera z-axis position. As I explained in this particular slide here, this is the position of the z-axis. Means our z-axis is going outside of the positive z-axis going outside of the camera or outside of the object. That only I am explaining here. So we determine z-axis with the help of view plane normal vector, right? Next we need to determine what is y-axis value. That is, we need to choose up direction of the camera. So that upward direction of the camera is called view up vector, that can be represented by using capital V. This is upward direction of the camera. As you can see this slide. In this slide, this is nothing but our Z view axis. And I am using green color arrow here. This green color arrow indicates this is our view YV axis. Means this vector is used to establish the positive direction for the YV axis. So this is nothing but YV axis direction. And this view up vector or look and up vector, this is nothing but our look up vector. I will discuss this in the last slide, right? Now we need to determine XV axis. So if you want to determine XV axis, X axis of the viewing coordinate, I said in the previous slide, using vector n and v, you can compute third vector u. So what is n means? N is nothing but our z axis. V is nothing but upward direction. Is nothing but this n is nothing but z axis. V is nothing but y axis. If you take the cross product of n and v, you will get u. Or to compute the third vector u means x axis, perpendicular to both n and v. Means if you draw one vector that is perpendicular to n and v, it will become x axis. So you see that clearly specified to define the direction for the xv axis. And that xv axis can be represented by using u here. Means we are using three vector u, v, n. U represent x view, v represent y view, n represent z view. So this is called u, v, n vectors. So here, as you can see that here u means x view axis, x direct x axis, v means y axis, n means z axis, and this p naught is a origin of the camera. Whatever I drawn in the left side, same thing I drawn with respect to camera. See that here, this is our, assume that this is our synthetic camera. In synthetic camera, I selected origin is nothing but p naught. From this origin, I calculated z axis, x axis, y axis. So here if you see this u v n, this u is nothing but x axis, this v is nothing but y axis, this n is nothing but z axis, n is nothing but z axis. So these are the four parameters I supposed to specify when I located synthetic camera in our OpenGL program. We'll move to next slide. We'll move to next slide. So this also I explained. This also I explained. Now we will see how to get different images with respect to projection plane. So as I said clearly, when I want to capture any object by using real camera or by using synthetic camera, in that object I need to decide one of the pixel position is nothing but my reference point, that is called fixed point. With respect to that fixed point as a consideration, I need to capture the image, right? Now assume that observer is standing here. Please you observe mouse point. Assume that observer is pointing here, our camera is located here. If your camera is located here, if your viewing direction is like this, please you see the mouse pointer. If camera is located here, if viewing direction is like this, means you are viewing this cup. The one teacup is there, you are viewing this teacup in different positions. If you are viewing this teacup with respect to this direction, assume that I placed projection plane here. So if you are viewing this particular teacup from this particular point of view, and this is your reference point, so when you capture this image, this cup image, this cup image is projected on the projection plane like this. Like this. You see that it looks like a rectangle or it looks like a square. See that this is our projection plane. Black color rectangle is nothing but our projection plane. Inside the black color rectangle, we projected one two-dimensional image, that is the cup image. It is projected. So with the help of projections, my intention is here, I want to explain, if I place the projection plane or if I change the reference point, then what type of images I will get on the projection plane. I am explaining that, right? Now what I will do means, I kept our camera here and I fixed my reference point P naught is here and I am looking toward this direction. Then I will get this image on the screen. Now what I will do is, we can keep the fixed point. I will set the fixed point here only. But what I will do means, I will change the position of the camera. I will change the position of the camera from this particular point to, see the mouse pointer, from this particular point to here. Here means how we are viewing this screen of the monitor. In that way, assume that we are viewing the a teacup that is displayed on the screen of the monitor. When we are viewing this teacup, assume that our reference point is same, P naught only, means we selected center position of the teacup. P naught is our fixed point. From that fixed point, I want to capture that image. So whatever the direction we are viewing that object, the teacup, that is the direction of the synthetic camera also. That is the synthetic camera, and assume that we located synthetic camera here and we are viewing this object teacup like this. When you capture this synthetic, when you capture this teacup, with respect to projection plane here or with respect to camera here, then see the what is the shape of the object we projected on the projection plane. So we'll get the another type of shape like this. Means just by changing the position of the camera, I am getting different images on the screen of the projection plane. Now what I will do means, again I will change position of the camera here. So if I locate the position of the camera here, means we are looking the teacup in this direction. Means we are looking teacup from left to right direction. Sorry, we are looking teacup from right to left direction. So assume that I located camera here. We are looking this teacup from right to left direction. Then see the how that image is projected on the projection plane. So what I would like to conclude here means, if you change the position of the synthetic camera, but if you fix the reference point same for all the positions of the camera, you will get different images on the screen of the monitor or on the screen of the projection plane. But in all three cases, our see that here we are changing only direction of the normal vector, right? So with respect to first position, our normal vector position is like this. The normal vector always perpendicular to the projection plane. Here in this example, our normal vector n, this is also perpendicular to the projection plane, and here also normal vector n, it is perpendicular to the projection plane. So what I would like to conclude with respect to this slide means, to obtain a series of view, means to obtain the different scene of the object, we can keep the view reference point fixed. Means our p naught reference point, we need to fix it, and we need to change only direction of the normal vector n. We will get different views of that particular object on the projection plane. So this is a one more example. Here in the first example, we placed camera here. We will get one type of image, and this normal vector is perpendicular to the projection plane. Now what I will do means, I will change the position of the camera to the second position. Again I will get different image. Again I will change the position of the camera to third position. In all three position of the camera, our normal vector is at the different locations. So different locations of the normal vector will create different shape of the that particular object on the screen of the monitor or on the projection plane. So these are the few terms with respect to viewing coordinate system. So next we will see how we can represent viewing coordinate system in a UVN coordinate system. So we need to setting up the viewing coordinate system and the view plane here. So assume that n is called view plane normal vector, and it is always along the ZV axis. Already we learned this, and I am repeating and I am revising, but it is a new topic. N represent view plane normal vector, or it is also called n. It is small n, you can say that, or capital N, you can take that. Z axis. Capital N represents Z axis. Capital V is called view up vector of the camera. It represents upward direction of the camera, that is called Y axis. So capital V is interconnected to Y axis. U is a nothing but X axis. It is means it is a perpendicular to both n and v. So if you draw a vector perpendicular to n and v, you will get u. So if the unit vectors along capital U, capital V and capital N are considered as UVN, means small u is called unit vector, V is also unit vector, N is also unit vector. So these are the three unit vector we are considering. So this system is called UVN system. UVN system. Now as you can see that here I drawn blue color. The blue color Cartesian reference is called our camera coordinates like XV, YV, ZV. On that Cartesian reference frame, I drawn one red Cartesian reference frame that is called UVN system. So U represent XV, V represent YV, N represent ZV direction or axis. So how to get N? How to get N? So how to get U? How to get V means we are using cross product formula here. We are using cross product formula. First I will explain U. I will explain U. U means it is x-axis and the x-axis value I can represent U1, U2, U3. Right? You see that. To determine x-axis value U, we need to take cross product of Y and Z. Y means V, Z means N. So if you take cross product of the unit vectors V and N, you will get x-axis. So here U is a unit vector with respect to x-axis. I will write U1, U2, U3. This V represent unit vector for y-axis. I will represent V1, V2, V3. N represent unit vector for the z-axis that can be represented N1, N2, N3. Now I represented world coordinate system. I explained how to represent weaving coordinate system for the camera. Next, I explained how to represent UVN coordinate system for the camera. Now, last step here, third step. So, first step is what I said. First, we need to define world coordinate system of that particular object. Means provide the object description in the world coordinate system. This is the first step I said. Second step I said define the position of the camera with respect to weaving coordinate system I said. Third step is we need to map world coordinate system to the weaving coordinate system. Then only we can able to project three-dimensional object on a two-dimensional plane. So first two steps we completed. Representing position of the object in a world coordinate system, defining position of the camera in a weaving coordinate system. So to define camera position, first we defined one of the fixed point or origin of the camera with P0 with respect to world coordinate system. From that origin of the camera P0, we determined x-axis, y-axis and z-axis. Next, we have taken one reference point on the object and we captured that object with respect to various projection or by placing camera in various positions, we captured that object in a different shape but reference point is same but normal vector positions are different. So these are the things we discussed. Now I would like to go for third step. So in the third step we want to map world coordinates system of the object to the weaving coordinates of the camera. So when you perform these transformations, that is mapping world coordinates system of the object to weaving coordinates of the camera, then next step will become projecting three-dimensional object on a two-dimensional virtual plane using projections. Now I am discussing third step. So we'll move to third step. That is the heading is transformation of world coordinate system to weaving coordinate system. So before explaining this, I will assume that our object is there in the world coordinate system, that is X world, Y world, Z world. Please you see the mouse pointer. Assume that this is the object is present here and the position of the camera here and the camera having its own coordinates called x view, y view, z view, and we determine these three axes of the camera with respect to origin of the camera, and origin of the camera is taken with respect to world coordinate system, that is called p naught, and its position is x naught, y naught, z naught. Now when you want to map world coordinate of the object to the viewing coordinate of the camera, we need only two steps. Only two steps. First step I am explaining with respect to this diagram. First step is, see that, translate the viewing coordinate origin to the origin of the world coordinate system. So what is the origin of the viewing coordinate means? We know that origin of the viewing coordinate is nothing but origin of the camera. So origin of the camera is nothing but p naught. Now we need to translate origin of the camera or origin of the viewing coordinate system to the origin of the world coordinate system. So when you perform this translation, origin of the camera is coincides with the origin of the object in the world coordinate system. Origin of the camera is coincides with the origin of the object in the world coordinate system. Means assume that this p naught is translated from arbitrary position to the origin of the world coordinate system. So to perform this, I need translation matrix. That is the 4 cross 4 translation matrix. We need, I return one, first I am reading from the row wise, 1 0 0 minus x naught, 0 1 0 minus y naught, 0 1 0 minus z naught, 0 0 0 1. This is a homogeneous parameter. So we translated origin of the viewing coordinate system to the origin of the object with respect to world coordinate system. Next, we need to perform rotations. We need to perform rotations. So with respect to step 2, we supposed to perform 3 rotations. Why we need 3 rotations means, please you see that here. Why we need, second step is called rotation. Why we need 3 rotations means, we learned how to perform rotation where rotation axis is not parallel to any one of the coordinate axis. With respect to that topic, here I am explaining how to perform rotation. So assume that, please you see this second diagram. Please you see the second diagram. Origin of the world coordinate system is same as origin of the viewing coordinate system after performing translation. Now as you can see that, x world, y world, z world is there. This is our world coordinate system. And xv, yv, zv, this is our viewing coordinate system. So the position of the viewing, origin of the viewing coordinate system is coincides with the origin of the world coordinate system. Now I need to perform 3 transformations. Why we need to perform 3 transformation means, assume that there are 3 rotation axes are there. X v is called one rotation axis, y v is called another rotation axis, z v is called another rotation axis. Assume that all these 3 rotation axes are not parallel to any one of the coordinate axis, either x w or y w or z w. Then what we need to perform means, we need to perform rotations 3 times for this 3 rotation axis. So when you perform rotations 3 times with respect to x axis, with respect to y axis, with respect to z axis, then all this world coordinate system of the 3 coordinate axis will become parallel to 3 viewing coordinate systems of the camera. So this is the outcome. Means after performing rotation with respect to x axis, rotation with respect to y axis, rotation with respect to z axis, then a viewing coordinates of the camera will become parallel to the world coordinates of the object. So as you can see that xv will become parallel to xw, yv will become parallel to yw, zv will become parallel to zw. Then I can say that we completed transformation of world coordinate system to weaving coordinate system. So to perform this, we need one composite rotation matrix called R. So composite rotation matrix R, it is a multiplication of rotation matrix with respect to x-axis, rotation matrix with respect to y, and rotation matrix with respect to z-axis. As you can see this example I written here. So this is x-axis, ux, uy, uz. This is with respect to x-axis. This is with respect to y. This is with respect to z-axis, and this is nothing but our homogeneous parameters. So whatever I explained here, this is with respect to step 1 and step 2. So same example I would like to explain with respect to UVN coordinates. So with respect to UVN coordinate, how we need to map world coordinates to weaving coordinate system. Here also we need two steps. So first step I need translation. Second step I need to perform rotations to align our rotation axis like xv, yv, zv to the parallel to all three coordinates of the world coordinate system. So assume that first I need to perform translation. So whatever x, y, z I written, assume that this is the world coordinate system of the object. Next, assume that we have three coordinates, three unit vectors like u, v, n. So u is represent xv, v represent yv, n represent zv, as already we learned in the previous slide. Now I want to perform translation. So when you perform translation, then origin of the camera will become, or it will coincides with the origin of the world coordinate system. So outcome of the translation is like this. See the diagram. U, V, N is there. U means x-axis with respect to camera. V means y-axis with respect to camera coordinates. N means it is z-axis with respect to weaving coordinates. See that neither any one of the unit vector UVN is parallel to any one of the coordinate axis. Then I need to perform rotation. Rotation with respect to x-axis, rotation with respect to z-axis, rotation with respect to y and z, x and y and z. So when you perform rotation with respect to x-axis, y-axis and z-axis, it is nothing but we are aligning our rotation axis has to become parallel to all three coordinate axes like x-axis, y-axis and z-axis. So finally we will get rotation matrix like this. So this is called composite rotation matrix with respect to world coordinate to weaving coordinate system. So we will get this is the matrix. Now finally I would like to conclude this topic. Finally I would like to conclude this topic. Here I am comparing whatever the terms today I explained with respect to synthetic camera to the terms we are using in our real camera. So try to see the heading. Effect of changing weaving parameters. So what are the effects we can able to see when I change the weaving parameters? So first point I written, when I am changing weaving distance. Weaving distance means weaving distance is a distance between the camera and object, or I can say that weaving distance is a distance between a camera to the projection plane. So what is the side effect we will get if I change the weaving distance? Means changing weaving distance in real camera, it is equivalent to moving object near or far from the camera. See that here. The beauty of synthetic camera, see that here. When you change the weaving distance in our OpenGL program, it is equivalent to moving object near to the camera or far from the camera. So this is the effect of zoom in and zoom out. So we learned with respect to viewport. What is zoom in and what is zoom out? So when you want to perform zoom in and zoom out, then we need to change the viewing distance in OpenGL program. Second example, when we are changing view plane normal vector, practically we have observed the teacup example. When we are changing view plane normal vector, it is equivalent to taking photograph of the object from different orientation or direction. So this is one simple example I already explained. See that when we are changing view plane normal vector in our real camera, the effect is it is equivalent to taking photograph of the object from different direction or different orientation. That is the meaning here. Third example, third side effect. When we are changing view up vector, it is equivalent view up vector means it is upward direction of the camera, we learned, right? Now if I change view up vector, what is the side effect means it is equivalent to twisting or rotating camera. See that here, orientation of the camera I discussed. So view up vector is required to twist the camera or rotate the camera so that I can capture the complete image of the particular object. Like this is the changing view up vector. When I am changing reference point, it is equivalent to taking photograph of the different part of the object. See here, here changing view plane vector, it is equivalent to taking photograph of the object from the different angle or different direction. If you change the reference point, if you change the reference point of the particular object where the image has to be captured, it is equivalent to taking photograph of the different part of the object. Means object is same. Assume that one object is there, that object having various parts. So whenever you want to capture that various parts of the object with respect to that particular part of the object, you need to consider reference point and you need to capture that particular object of that particular we need to capture that particular part of the object like this. So these are the practical things we are discussing with respect to real camera as well as synthetic camera. So today we discussed only what are the camera coordinates and what are the coordinates with respect to object. So I would like to conclude today's class. Today we discussed only 3 steps. Tomorrow we will be going to discuss fourth step. So what is the first step we discussed means? First step we discussed how to define position of the object in the world coordinate system. Second step, we define position and orientation of the camera with respect to viewing coordinate system or camera coordinate system. This step is also includes position and orientation of the projection plane, where we need to locate position plane. There are 3 different positions are there where you can place the projection plane. So this is the first thing we determined. Next, with respect to second step, with respect to camera coordinates, first we decided what is the position of the camera by defining fixed point or origin of the camera, that is called P0. So once we defined position of the camera with respect to world coordinate system, that is called P0, then we calculated what is the x-axis, y-axis and z-axis direction with respect to camera position or with respect to viewing coordinate system. Next, we discussed how to map world coordinate system to viewing coordinate system. So once you map world coordinate system to viewing coordinate system, only one more step we need, that is called projections. So with the help of projections, we can project three-dimensional object on a virtual plane or on a projection plane so that we can display that image on the screen of the monitor. This process is called three-dimensional viewing. So today I completed three steps. Tomorrow we will see what is projections, how we can use projection to project three-dimensional object on a virtual plane or on a projection plane. Thank you.